Hey everyone, so in today's video we're going to go over partial fraction decomposition and a practice problem. So the idea of PFD is that we can take fractions and split them into easier parts that might be nicer to work with. So a motivation for this is you already know the reverse of this. So you might have been asked a problem like 1 over x plus 1 over x plus 1, and you've been told to combine this fraction. So you know this by making a common denominator. You want both of these denominators to be the same so you can add them together. So multiply this 1 over x by x plus 1 to get x times x plus 1 in the denominator. Then multiply 1 over x plus 1 by x on the top and the bottom, of course, to get x times x plus 1. And now you can simply add across and you get 2x plus 1 equals x times x plus 1. This is something you all know how to do, and it's called finding a common denominator. Now the question is, if we had something like this, could we get back to here? Because when it comes to calculus, doing something like the integral of this is much easier than doing something like the integral of this. Actually ends up working out nicely in this case, but there are cases that you'll see where it's much harder. So let's think about this. Let's look at a quick example. Let's say we have something like this huge fraction, x times x minus 1 squared times x squared minus 2x minus 3. Okay, this would be a complete mess to integrate. There would be no way we could possibly do this. Now, if we think about partial fraction decomposition, what might this look like? Well, knowing how it was earlier, it's going to be something of the form a over x plus b over maybe x minus 1 plus c over x minus 1 squared. And finally, plus dx plus e over x squared minus 2x minus 3. Okay. So let me explain how I got to this. This really is kind of a rule you have to memorize. The actual reasoning comes from linear algebra, but at this point you're just going to have to kind of accept it. So whenever you have something called a linear factor is something like x minus a to, I guess, the n for some exponent n is greater than or equal to 1, right? So x here is a linear factor for a equals 0 and n equals 1. X minus 1 squared is a equals 1, n equals 2. So these are linear factors because you have a linear equation, right? You don't have any quadratic and any cubic, you just have x to the 1. So we call it a linear factor, and linear factors are pretty easy. If n is 1, well, you only include it once here, like a over x. If n is per se 2, then you gotta include x minus 1 to the 1 and x minus 1 squared. If it was cubed, you would go x minus 1 to the 1 to the squared, all the way to the cube. Now, you could also have a quadratic factor. Sorry, that was a horrible cue. So in this case, we have one quadratic factor, and in general, they look something like ax squared plus bx plus c. The reason why we sometimes have these quadratic factors is that a quadratic is kind of the smallest, or it's kind of the largest polynomial that sometimes can't be broken into parts. So as you know, there's some polynomials like x squared plus 1 that you just can't factor, right? Unless you introduce complex numbers, of course. But we're working with real numbers here. So you can't factor this. So we just have to accept it as another factor, right? In our partial fraction decomposition. So we give it a whole nother term. And the same applies when you raise this to the n power. You got to do it to the 1, to the 2, then to the 3. And something else is different. You see, for here we just have a, b, c, but here we have dx plus e. And the reason why we have this extra x here is because, in general, since we have a square here, it's possible to have a linear factor up here as well. This comes from the idea of polynomial long division, where if we had something that was like x cubed, we could do polynomial long division. The smallest possible thing would be something with an x. So we sometimes when we solve it, d ends up being 0, x is not involved. Maybe you just have an e term. But we just have to have it there just in case it is involved. And we'll see that it will get involved in the practice problem that we try out. So you're just going to have to memorize how this works. Hopefully that shouldn't be too hard. It's pretty straightforward. So let's try an example. This should be number 7 from Paul's online math notes for partial fraction decomposition. Number 7. So he's asking us to find the integral of z squared plus 2z plus 3 2z plus 3 all over z minus 6 times z squared plus 4. Okay. So let's see what we can do here. First, what I'm going to notice is that this is a mess to integrate, right? It's just not going to work out. So we should probably try to do partial fraction decomposition. And we should notice we have a linear factor here, LF, and here we have a quadratic factor since we have a z cubed. Or z squared, sorry, quadratic factor. So we know our function z squared plus 2z plus 3 over z minus 6 times z squared plus 4, 6 times z squared plus 4, is going to be of the form a over z minus 6 plus bz plus c over z squared plus 4. Okay, this is the start, right? This just comes from the algorithm. Now the next step is when we actually start to do some algebra, okay? So how could we possibly solve for this? I mean, just to have a check, we're trying to solve for a, b, and c, right? If we know those values, this is actually something that's very easy to integrate. So how could we find them? Well, one trick, and basically the universal trick we have to try in this case, is multiplying by this denominator on both sides of the equation. The reason why we do that is because it'll cancel out here, and we'll get some nice cancellations over here. So let's see what happens. So clearly we get z squared plus 2z plus 3 equals the z minus 6 cancels out with this z minus 6, and we get a times z squared plus 4. And we get bz plus c and then the z squared plus 4 cancel out with that, and we get z minus 6. This is great, but also not really. I mean, it feels like we didn't get anywhere. Luckily, we kind of did, because now there's kind of a trick to this kind of problem, and I'm just going to have to show you how to do it, and then you can use this trick. So we're going to factor the right side in a slightly different way. We're going to say, first of all, let me just multiply this all out to make this as clear as possible. az squared plus 4z plus bz squared plus negative 6b. Oh, now I have a 6 and a b. 6b z plus cz minus 6c. Okay? Now let me factor it like this. Z squared times a plus b then we get z times, what should we have? We should have, this should be a 4a right here. That's what was confusing me. Z times c minus 6b. And then finally at the end, we're adding something like 4a minus 6c. Yep. Perfect. So here's the trick. We have two polynomials, and let me rewrite this down here. 1 times z squared plus 2 times z plus 3. So let's just acknowledge that what we're saying here is that this equation is true for all z. Every single z we pick, this equation is true. Okay? Now, technically, according to linear algebra, we can do the trick where we now know that we can equate these coefficients. We know that 1 must be a plus b. Let me use colors here to really illustrate my point. 1 and a plus b must be the same. 2 and c minus 6b must be the same. And 3, it's going to be hard to see. 3 and 4a minus 6c must be the same. So this stems from linear algebra, that we can equate these coefficients. But let me just try to briefly, convince you that this might be the case. So what if I subtracted over z squared plus 2z plus 3? I get something like 0 equals z squared times a plus b minus 1 plus z times c minus 6b minus 2 plus 4a minus 6c minus 3. Perfect. This is 0 for all z. Okay? Every single z we choose, this is the case. Okay? So, there's a couple ways we can reason this out. One argument is that, okay, let's let z go to infinity, right? Z squared plus z plus all of this is going to be huge, right? If z is going to infinity. And yet it still equals 0. I mean, reasonably, when you think about it, the only way that could be possible is if all of these coefficients are 0. Right? The only way, if z is going to infinity, can these coefficients be 0. Okay? That's the only way this equation could ever be true. What that means is that we get a plus b equals 1, c minus 6b equals 2, and 4a minus 6c equals 3. Same idea here with equating the coefficients. Red to red, blue to blue, black to black. Another argument is this. What we have right here is a quadratic, right? Z squared plus z plus something. Quadratics have 2 roots, right? That's just what we know. Quadratics have 2 roots. And yet, a root is when the function equals 0, the polynomial. But we're saying this equals 0 for all z. There's infinitely many roots. A quadratic cannot have infinitely many roots. So obviously this function cannot be a quadratic. In fact, it can't even be linear because lines only have 1 root. So this function has to be what's called the 0 function, the thing that equals 0 everywhere. That's equivalent to saying, well, you have 0z squared plus 0z plus 0. Well, that's just 0, right? So if some polynomial has more than 2 roots, some quadratic has more than 2 roots, it's actually all 0. And in this case, it has infinite, so it clearly is all 0. So basically, to make this short, what we're saying is we can equate these coefficients. We get a plus b equals that 1 on the z squared. We get c minus 6b equals that 2 on the z. And finally, we get 4a minus 6c equals 3. Okay. That seems like a lot of work, and we're still not done, because now we have this, which looks kind of weird, right? I mean, it just seems like we haven't done anything for ourselves. Luckily, this is something that we can do. So this is called a linear system of equations. System. Hopefully that name brings back some bad memories for people who took the SAT, because these kinds of problems are classic on there. Unfortunately, this is a slightly harder version of an SAT system of equations problem, but let's try to solve it together. So the first step I would take, and generally when you're doing these, is you're going to try to isolate certain variables. You're going to try to cancel things out. So let's work these first two equations. Something I notice is that we're having a minus a b and a plus a b. So let me multiply this top equation by 6. I get 6a plus 6b, 6b equals 6. And I get c minus 6b equals 2. Now if I add these equations together, I get 6a plus c equals 8. Okay, great. New equation. Now, let me look at this third equation. 4a minus 6c equals 3. We could do the same trick with multiplying the c's, and I recommend you try that out. In this example, I'm going to try to cancel out the a's. So multiply this top equation by 2. We get 12a plus 2c equals 16. And I'm going to subtract the bottom of equation times 3. 12a minus 18c equals 9. And that idea came to me because I see I have a 6 and a 4. I know that their least common multiple is 12. So multiply this one by 2, multiply this one by 3, and you're going to get two 12a's. Subtract them. You get 20c equals 7, and you get c equals 7 over 20. So this is great. Okay, we've solved for one variable. The others are going to fall real fast. So let's look at this equation right here. Now we have 6a, and we can plug in c to be 7 over 20 equals 8. That then gives us 6a equals 153 over 160, and you can figure that out in your head if you want to. Wait. This should be over 120, not 180. Right? No. Equals 6a plus 720, subtract over 720, then you get 160 over 20 equals oh, I see what I did. Yeah. So this is not a 6 anymore. This should just be a. A equals 153 over 120. I subtracted over 7 over 20, and you get 153 over 20 divided by 6, and you get 153 over 120. You can simplify this to be 51 over 40. So now we know A is 51 over 40. And finally, we're going to use our top equation, A plus B equals 1. Plug in A to be 51 over 40, plus B equals 1. Then we know B to be negative 11 over 40. So now we've solved for A, B, and C. Perfect. Our problem is basically done. Now just remember what our original equation was. Original equation was A over, let's actually go back up and look at it. So our original equation was A over z minus 6 plus bz plus c over z squared plus 4. So A over z minus 6 plus bz plus c over z squared plus 4. Now you plug in your points. You plug in A equals 51 over 40, negative 11 over 40, and 7 over 20. And this is actually an integral you can solve now. I won't work it out because it's something you should be able to do on your own. If you're confused with this term, try splitting up the numerator into something that looks like arctan and another thing that looks like a u-sub problem. So hopefully that was helpful in understanding how to do partial fraction decomposition and a challenging example. Thanks.